Só não explicou pro gringo, não é isso? A melhor coisa, cara, que você tá com um gringo na sala, que você fala que o Christopher, por exemplo, ele sabe que de algum nome dele, né? Aí fica olhando, você tá falando de mim. Eu não faz a menor ideia, cara. Ele tá falando, todo mundo rindo na cara dele e não sabe por quê, não sei. Ai. Hi, Chris.
I can guess a couple of things.
I know you can. Okay. E aí, para minha última... Are you all set?
Oh,
all right,
yeah,
okay.
I guess so.
E aí, minha última pergunta para vocês, pessoal, é o seguinte. A gente esqueceu, né, falha minha, na verdade, eu esqueci da gente pensar na tradução simultânea. E aí eu queria fazer uma pergunta honesta, tá certo? Né? Se tem alguém aqui, eu vou fazer a pergunta contrária, assim, né? Qual eu deveria perguntar, né? Qual que eu pergunto? Sim ou não, né? Eu vou perguntar assim, quem precisa de tradução simultânea, honestamente, aqui? Ninguém, né? Uma pessoa só. Beleza, então nós não vamos fazer tradução simultânea no microfone, certo? Mas se você quiser sentar aqui na frente, ou alguém mais quiser, eu posso fazer tradução para você. Ok? Tá certo? Porque assim, normalmente a gente traz um radinho para fazer tradução simultânea, a gente esqueceu de avisar isso antes, mas podia ter vindo mais gente, né, que precisaria de tradução se a gente tivesse avisado, mas eu esqueci, tá certo? Né? E aí a gente, na verdade, nem trouxe o equipamento. Então, beleza. Se você quer sentar aqui comigo, eu faço a tradução para você, beleza? Fica tranquilo? Tá bom. Então, sem mais delongas, tá certo? Christopher, né? Agora ele vai saber que isso aqui é o que eu estou falando dele mesmo, tá certo? Né? Queria apresentar aqui o Christopher, não tem, I don't have your bio, but I'll just, does it, right?
Yeah, it's not bad.
Okay. Not impressive? Okay. So I'll just talk, yeah. Então, assim, falou que não é muito impressionante, né? Mas o Christopher trabalha na Hazelcaster, né? Que fornece uma solução aí de processamento distribuído, certo? Né? Alguém sabe o que é isso aqui, não? Agora os nerds estão sabendo aí, não? Né?
Does anybody know that?
Quem sabe o que é isso aqui, não? Mais ou menos, não?
Todo mundo googou antes.
Oi?
Todo mundo googou antes da palestra.
Não, quase ninguém sabe. Então, you're gonna have to explain what it is.
Okay.
Because most people didn't get it. All right.
Always the same thing.
Yes. Our coder belongs to us, right?
Yep.
Yes.
It's cache.
Yeah. Our cache in your case, okay. Our cache belongs to us. Mas assim, então assim, a Hazelcaster faz uma solução de cache de processamento distribuído, super bacana. Eles foram eleitos para o board do JCP agora recentemente, certo? E aqui a gente vai ter uma palestra super bacana sobre computação distribuída. E o Otávio queria que eu fizesse agora, mas o Chris falou que ele gosta de ter mais tempo para falar das coisas e tudo mais, que ele curte bastante, né, grupos de usuários, que você não tem uma hora certinha, não sei o que. Eu achei meio sacanagem falar para isso de uma hora, tá certo? Então, vamos dar um pouquinho mais de tempo para ele aqui e a gente termina fazendo um bate-papo sobre Java aqui depois, ok? Beleza? Então, com vocês, Christopher.
You know that you have to explain everything afterwards, right?
I know.
What, every single sentence that had Chris in it, you have to explain.
That's why I got my talk afterwards. So.
Perfect. I see. Okay, so short bio. I'm working with Hazelcaster since November 2013. I've actually worked at some travel agency before HRS. It's one of Germany's biggest hotel reservation systems. That's what HRS is, Hotel Reservation Service. I worked at Ubisoft doing low latency game server programming and a couple of other things that normally people don't want to do, like GC optimization, unsafe stuff, and I probably shouldn't name the unsafe stuff. Okay, so distributed computing with Hazelcaster. Let's say it's a bit of distributed computing in general. What are the general terms to have a nice distributable system? And all the examples will have Hazelcaster, and somewhere maybe someone will figure it out. Somewhere is Shane's block of Hazelcaster itself. So first of all, the thing should be interactive. Interactive means, well, you can start, stand up and start dancing. I figure out that it seems to be very Brazilian. On the other side, whenever I do live coding, I want everybody to listen, to look, and whenever I do a mistake, I make a lot of mistakes, tell me. So to learn how interactive works, we start with a little game. So I ask you a question, and everybody answers yes. Is that clear? Perfect. So did everybody read that?
Yes.
Perfect. Awesome. That works amazingly. Well, yeah. So that's me. Just name me Chris. Whenever someone wants to have a lot of stuff going on Twitter, follow me. Whereas the last days were a bit quiet. I'm doing Java for 9+ years, 10+ years. I don't even count it anymore. And as I said, well, performance, GC, all kinds of Java fairy tales, Apache committer, whatever. And if somebody wants to look at my blog, which is reasonably often updated, there's either sourceprojects.org or the better domain, which is Hazelcaster. I like mostly the top level domains. Okay, so distributed computing. I guess everybody has like his own data center at home, doesn't it? I mean, everybody has to make, well, maybe someone has a new PS4. No? Okay. But a couple of old computers, new computers, laptops, whatever. And actually, there is a better way of describing what a data center might look like in the future. Did anybody ever thought about that? Especially the power grid. I'm not sure how it is in Brazil. In Germany, we all over the place install those intelligent power counters that are somewhere, and they are all connected, and whenever there's a virus, the whole power system goes down. Different story. So, okay, the cat picture that every slide that means. What does distributed computing mean? First of all, it means we want to scale out. We want to distribute our operations on commodity hardware, a lot of hardware, instead of going the Oracle way and just trying bigger and bigger, or selling bigger and bigger machines. I'm not saying that the right one is Oracle, but everybody can believe it. So the second thing, and this is more Hazelcaster specific, it's not essentially distributed computing. Hazelcaster is an in-memory data grid. So what we do is in-memory computing. In-memory computing. Why do we in-memory computing? Because memory is cheap, or reasonably cheap these days, and it's way faster. So for example, if you think of sending a package between California, Amsterdam, and California, 150 milliseconds is probably not what you want. And I guess Sao Paulo, Amsterdam, Sao Paulo might be even worse. I know at least that Mexico is pretty bad for latencies, at least to Europe. We're not as good as L1, L2 cache, obviously, but we're pretty close with the main memory references. So main memory is what Hazelcaster is looking for to do. The more RAM you get, the more data you can store in memory, the faster you can compute, the faster you can compute on those data in memory. That's the sentence I want to say. Well, it's still okay if you go to SSD. If you don't have enough RAM, you can overflow to disk, but you want to prevent those things as much as possible. Whereas if you for example use Hadoop for operations, SSD is the typical case, but Hadoop solves a different problem. Hadoop is more like doing nightly runs, doing non-real-time computation. So Hazelcaster is more about in real-time, in-memory computation. You just fire up a request and you try to get the data as fast as possible, or the result as fast as possible. And as I said, well, the memory size is constantly going bigger and the prices get reasonably cheap. So there's not a lot of problem. This chart ends in 2013 and there's a megabyte by less than a cent, a half a cent about. 16 gigs per module was typical for server. think the newest systems have more like 64 gigabytes per module or something like that. I somewhere stopped looking at it. So what do we do is data distribution. That is an essential thing for distributed computing. You have to shard data, you have to partition data, then it makes sense to split your operations into multiple chunks. This microphone holding stuff is pretty bad. Distribution of data. Imagine you have a cluster of 10 nodes, and every of the 10 nodes holds either all of the data or at least a part of it. And the overall split, if everybody holds a part, gives you your whole result set. So, for example, what we do is when you want to store something, you have a code or a key, and you put it into a map. And what we do is we take the key or the code. Hazelcast itself serializes it internally, but in this case it's not important. We take a hash code, a consistent hash code of the key, and then we have a fixed amount of partitions. And what we do is we take the hash code, which is always the same because it's consistent hashing, and we use the mod operator and say, hey, this is my number of partitions. So what partition does that key belong to? And then we just send it to the partition. That means whenever someone requests or updates or sets or removes the same key, it will always end up in the same partition. That's the beauty of the thing. So if we look at it, what is important, as I said, it must be a consistent hash function. This is the main part, otherwise you have to figure it out differently. The partition count must is not exactly true. It should be constant. Whenever you have a system where you can change partition count at runtime, it means it has to redistribute everything, it has to repartition everything. There are systems that do that, Hazelcast doesn't, because we say it doesn't make sense. If we have to send all the data around, we can shut down the cluster and restart it. And the nice thing about, at least for us, is we can do some smart routing. So we have two topologies. We can have embedded systems where every of your application is part of the cluster, or you have a more database setup, well, database-like setup where you have a separate cluster and you have clients connecting to it, like JCP. And with this thing, the beauty is that the client can figure out where to send the operation. So you prevent these nice hopping where you send it to one member of the cluster and member says, oh, I'm not the one, but I'll relay it for you. So you don't have to do that in most of the cases. If that makes sense. we can show it properly. So I see you're not looking like that yet. So that is probably a good thing. We can cover that. That kind of works. Okay. I think I can also just speak loud enough. That should probably work.
It's
Better to talk to the microphone. Okay. We want to do data distribution, so let's call it data distribution. And we do very, very important logic. So we start with something simple. We start up a Hazelcast cluster. As I said, all of the examples use Hazelcast, somewhere is a shameless plug. And the beauty for Hazelcast is it's very easy to set up. That is the main difference from all of our competitors. If we start up that, we get a Hazelcast cluster. If we start it up multiple times, we get multiple members. And just to prove it, I hope it works. I definitely deactivated the Wi-Fi, just in case. So we have one member, and I start up a second one, and there we have two members. And if I start up a third one, You see it connects two sockets. It will actually join together and build 3-member cluster. So we actually have a running Hazelcaster cluster on this laptop now, a 3-member cluster. What it does is, the black magic behind is Hazelcaster by default uses multicast to figure out if there are other members somewhere in the reachable cluster or in the reachable network area. Obviously, not every operation guy, network operation guy. Do we have network operators here? No? Okay. Those guys normally don't like multicast because it breaks their system. It was not designed to be used in networks. Nope, it has to be designed for something else. I don't know for what, but it seems to be something different. So what you can do is you can obviously configure IP addresses. We have support for AWS Discovery. And with the new version, there comes Discovery SPI where everybody can build his own discovery provider. For example, build based on Zookeeper, on any kind of other service discovery. Microsoft is building, what is this thing called? Azure? Does anybody know that? Uses that? Okay, you break my joke. Everybody says yes by I know, but nobody says yes when he is.
I have to use every cloud provider. So.
Okay. Yeah, so Microsoft is very eager to get an Azure discovery mechanism into a Hazelcast. I don't know who wants to run Java on Windows, but whoever wants to, there is definitely a way in the near future. Out of the box. Okay, so let's go back to our example. Hey, the beauty about Hazelcast is we're trying to be as easy and as Java-like as possible to any kind of Java developer. So we have a map, whoops, and let's do it that way. And normally we would do something like this, right? We would say, okay, I want a hash map. Okay, how do we make this thread safe? Right, we use a concurrent hash map. How do we make this thing distributed? We say Hazelcast, give me a map, and we give it a referral name, which we call data, for example. That's it. So Hazelcast implements all these standard Java interfaces as much as possible. We have a couple of features where Java doesn't have something, therefore we can't extend the Java interface. But in typical cases, that's what we do. And that means we really use it as Java. So we create like 1,000 keys. Whoops, 1,000 keys. Nobody complained, I made a mistake. And don't tell me I was too fast. And we put in a value. And if I leave that running, it will do exactly what you expect. It will create a cluster map. It will create a map somehow, and it will put in 1,000 values. That's it. So we can leave that running. Obviously, it doesn't really make sense at the moment because we can't see anything. But we see it says in the last line, initialing cluster partition table. That means we actually put something in, Hazelcast figure out, oh, I don't know where the partitions are yet, so I need to create a partition table, and then it put in data. Okay, we want to make this a bit more visible, right? So let's put in some sleep here and start that up. It's still not very visible, not yet. But now we come to the nice part. So Hazelcast extends the Java interfaces wherever it makes sense and adds distributed features. Distributed features could be a distributed query, like a SQL query, a predicate, whatever. Things you know maybe from Google Guava, something like that. But it also has another nice feature. It has listeners. So in a distributed environment, I maybe want to know if somebody else does something with data structures. I want to inform about it. So I say, well, I want to have an entry at listener, integer string. And now we do our very, very important and very obvious business logic. And we say, okay, please add me a message listener. And we want to see the value. So the second parameter tells this cluster, okay, I have a listener, and I might have values which have 100 megabytes. I'm really just interested in knowing that the key was added, the key was updated, but I'm not interested in the value at all. So just pass in faults and save a lot of memory traffic. And well, we still have our first system running, or first instance, and I start the second one. And who can guess what happens? We hopefully get events that are put in by the first node. So this at the moment keeps all or gets all the information. So whichever of the two members gets the data, I will get the event. Maybe not exactly what I'm interested in. Maybe I want to have more like the local entry listener. Oh, I think that's it. So in this case, I only get events whenever something happens locally on my machine. So, for example, I want to react on a key added into a map because I want to do further computation on top of it. Computation only if something happens on my node, because I'm not interested in the others. They can do their own stuff. So now we get way less events because we just get half of them. The other ones are still at the other node. That doesn't show anything yet. So we see that partitioning really works in this case. Some nodes or some data are on the one node and some on the other.
What happens with the first 100 items that were there? Because you added a new node and then the hashes.
Yeah. By default, we have one backup. So that means I can even.
But you had 100 items in the map. In the node that's still running, and then you add the second one, so that changes the routing.
Oh, okay, yeah. So what we have is we have more partitions than nodes. We have a partition table that says, okay, this partition is currently owned by that node. Whenever someone joins, we recalculate the partition table and move partitions to the members that joining the cluster. If someone's leaving the cluster or is failing, we take the backups, reactivate them, and again, doing the migration. So, for example, I can still prove that that the data is here. So I can say, please give me the value for 100, and hopefully it should give me a fairly reasonable result. No, okay, not very reasonable. Why? To be honest, I don't know. It should print value 100. Let me guess. Give me a second. Max size, no. Okay. Backup should be activated. I don't know. Who can spot the error? We were over 100, don't we?
I think the 100 started in the second instance.
No, the problem is we need to have more than 100 seconds to have a 100. Maybe we weren't far enough yet. Oh, there you go. Maybe that was the problem. There weren't 100 seconds yet passed by. Okay, back to the. Okay, I think everybody agrees that it wasn't that bad. So why it wasn't that? We're trying to stay as close as possible to Java. Our main purpose is we want to prove to Java developers. Well, we have C++ and C#, but we want to prove to Java developers that distributed computing doesn't need to be as hard as systems like Spark or Hadoop or whatever. If you ever look only Otavio has a notebook for that. What? Herman? Okay, the second thing, parallel processing. After we distributed our data very nicely in the cluster, hopefully mostly equally, we want to do some distributed computing. Distributed computing has a fairly important rule. It needs to be independently computable. So that means if we're not looking at a distributed system, but first looking into something which is fairly easy, we generate 100,000 random integers. This is, by the way, not Scala, this is not Java, this is something I made up of. I think there's a bit of Groovy, a bit of Scala, and a bit of Java. So 100,000 random integers, and we split that into blocks of 10,000. And those 10,000 blocks, we can sum them up totally in parallel. We can sum them up serialized, one after another. We can sum them up on different nodes, nobody cares. As long as the result will always be the same. And then we take those intermediate results and generate, or sum them up to the whole overall system. So the important thing is, we don't want to have mutations. For everybody who's coming from functional computing, do we have functional programmers here? One? Wow. I guess this is nothing new for me. No mutating values, only create new ones. A small problem for the JVM sometimes. The JVM doesn't really like new objects all the time. Whoever tried to split up a long string in tokens or chunks or whatever probably knows what I'm talking about. But hopefully with Java 10 finally, Java 9 doesn't seem to be working anymore, we get value types, and value types will give you a nice feature of those things, especially Arrays 2.0. And I haven't written a book, but next week on Monday there will be an InfoQ article about the world after some is unsafe, after the post-apocalypse. And I try to figure out what are the proposals and to show how Java might look like in the near future. And one of those things is value types and arrays 2.0. Finally, it means we get arrays with long index. Did everybody need that? Yes, I do. Nobody else? Okay. Fair enough. So, as I said, no mutation, independent, computable. It doesn't matter where we compute those intermediate results, and it really doesn't matter where we compute the final result. We can just send it to another node again and wait for the result. We can send the last sum operation together with a callback or whatever, and say, hey, whatever happens or whenever someone finished this, please do the next step, whatever it is. Okay, again, so sorry. Not. So, let's call this processing, and again, whoops. Oh, wow. Ooh, I found a new shortcut. And again, we start a Hazelcaster cluster. I think everybody figured out so far how it works. By the way, I had a configuration file open where it just looked in. So what I do here is, as I said, I deactivated my Wi-Fi. But on some conferences, you don't do that. And the only thing I'm telling the system here is, hey, whenever you try to figure out other members, please do them on local host only. Otherwise, if somebody here puts out his laptop and starts a Hazelcaster cluster, he probably will join the same one. And that screws up my presentation. Just has to be 100. So this is one of the ways you can configure it. You can also use 192.168. ** or something, and then you just figure out nodes in the same subnet, whatever. There are a couple of ways to do that. Back to our computation.
We want to have random. And we need values. Java 7, thank you. Finally, somebody can read it. Does anybody does that in real code? Wow, you should definitely should. It makes things easy, readable, doesn't it? It makes it fairly readable. I mean, it looks weird if I do that. And now we need a split function. I should have prepared that. That doesn't work. I know how my we have 10 blocks, right? New MacBook, different keyboard. Yay. That looks like amazing code. Don't do that at home. Why do we need to initialize Java arrays? Who came up with that idea? I think so, right? Next time I prepare this split operation. And we get an executor service. And even here we ask Hazelcast for something. What we do is, let's make it obvious. Public static class. Some class. Permanent switching between Windows and Mac is not a good idea. Don't do this. Doesn't that look like nice in slides if you just made up your own language? And we submit it. It could be so easy. It would be probably easier with the Stream API. Yeah. Well, next time. Next time. I promise. At least we have a diamond operator. At least we know why we have those nice Java features. Yay! I think I got it. Wasn't that easy? Should we go back to the slide? So I pretty much created 3 lines of code in Java. This is the perfect example for everybody who says Java is verbose. Yes, it does. Sometimes. As I said, it might have been easier with Stream API. And actually, it doesn't make sense, but wait. First. Let's start off with Node first. That we see that at least something is going on. Start with the second node. And hope that it actually works. Null pointers, still connecting, 3 nodes, okay, whatever. And we get a null pointer, obviously. Oh, yeah, okay. Probably the first block would be initialized. I think everybody got the idea. That was definitely a good example. So let's see. The real problem is it works. I think that should be. No, this is not true anyway as well. Whatever. I think everybody got the. So what happens is, let's just explain it. So I create this executor service, so I'll ask Hazelcaster for an executor service. And it's the standard Java executor services again. So that means you can use the standard submit and execute operations, but we have again some more extended versions. So you can say, I want to send it especially to a member that owns that key. I want to send it to the member because I know I want to send it to that member, no matter if he owns the key or not. You can implement your own load balancing algorithms by implementing member selectors, which all the time implement or return different members to run on. Or you can say, hey, I have an operation, I want to send it to all members to gather statistics over the cluster or whatever. So in this case, it will just do a randomizer, and it will take all the cluster members and send the operations just to the cluster members, to a randomizer one. In a big cluster, that means you get a fairly good amount of randomization. For a real world use case, you might want to implement your own load balancer. Did anybody ever implement a load balancer? No? Okay. Most of the time people ask, why don't we do load balancing on our own? And I did a very complex one at Ubisoft. While players were loaded when they first logged in, we had to load all the data into RAM and kind of things. And load balancing is not an easy task. You have to know a lot of things about the operation, how long they might take, how much RAM is available, how much CPU this task might take. It's not a thing that can be generalized, or not an easy that is. So that's the reason why I personally, I'm the one to blame if anybody ever wants to have a generic load balancer in Hazelcaster that is not random. Because everything else that you implement in weeks and hours will anyways look random to everybody else. Okay, do we need to get this running, or does everybody believe it will work? I don't hear no. Okay. So I guess everybody would believe it. And now the next picture makes even more sense because it was absolutely easy. But the hard part was not Hazelcaster, it was the split operation. That's the reason why you don't use splits, not even with strings. By the way, as I said, I'm from Germany, and that's probably the best picture ever taken. Okay, to wrap this up, the last part of Hazelcaster and distributed computing is also distributed caching. Distributed caching for Hazelcaster is one of the biggest use cases so far. So we have a fair amount of users migrating from Coherence or Gemfire or all the other competitors out there. And those, most of the time, do computation. Those are finances, insurances. People that are using distributed computation for a long time. All the new customers that are coming to Hazelcaster and asking for something normally do caching. They have systems, they have caches maybe already, but all of these caches are normally local. That means all the nodes store the same data over and over and over again. But what they really want is, they want to have a fast access to data without hitting the database, but they don't want to duplicate the data all the time. Besides, you have cases where you really want to have this amazingly low latency of load call all the time. So why do we do caching at all? I think I don't explain something new. Now, yeah, you collect and store for the worst case scenarios, right? You want to collect for things whenever you access something that is necessary to be accessed fast. As I said, there are two ways. You can have a distributed cluster where you can have a cluster round trip, but it's still fast because the value store is designed to be fast accessed by key. Or you have those local accesses where you have local concurrent hash maps, and you not even have the cluster round trip in this case. If you have an embedded cluster, in the best case, you have local call because your key is stored locally. In the worst case, you have to do one cluster round trip. But those cluster round trips on our test labs, which is pretty much thing, probably not, it's not to be found anywhere in the data center yet. We have like 23 microseconds. So obviously on 40 gigabit solar flare. Nice things, by the way. Anybody wants to have a very nice data center by solar flare. Okay, I'm not sure how famous Big Bang Theory is. It is? Okay, good to know. So that works. Fun with caches. Who wants to have flags when you can have caches, right? Okay, so evolution of caches. I think a fair amount of people created their own cache somewhere in the recent past, or in So, I mean, custom caches are easy, right? It's just like roll your roll. By the way, don't ask me, this is a US invention. If you want to create your own hot dog, that's how it goes in US. You can buy those things, believe me. So, we all know caches are simple, right? This is a typical cache. You have an implementation, you have a current hash map, and, well, you have put and get. In the best case, you name the methods cache and give whatever. So that's it. So why do we wrap the current hash map? Well, at some point you might want to have things like TTL, time to live. A cache normally has an expiration time. So I want to have my keys expiring after 1 minute, after 10 minutes, after 24 hours. Those are the normal things. But operation will complain about that. Why? Because this, even if you can't read it, believe me, it's not meant to be readable. It does lazy expiration. So whenever I put or get something, and I either see it's full or the key is expired every minute. That means my Java view is constantly growing, up to the point where my max size is reached, or I only have dead keys. So, as I said, operation will only complain about that. Your Java process takes way too much memory, nothing happens on the system. Why doesn't it free the memory? Well, sure, we can do that. Just add some auto cleanup. That's very easy, right? Auto cleanup, it's a task running in the background, somehow figuring out if keys are expired, removing them. Well, okay, let's play another game. What is wrong? Let's see how many people figure out what is wrong on that one. And I need to be honest on that. This is not a made-up example. This is in one of the old versions of EasyPass. I haven't written it, but we actually found it by accident. Because we created a new system. So you can still try to figure out this wrong. Well, I'm giving a fair tip. So we create a new system, we call it Simulator. It is meant to create a system load that looks like a real-life operation. And whenever we release a version, we need Hazelcaster running in the simulator for at least 48 hours. So what happened is, and now, did anybody figure it out? No? Okay. I'll give you a hint. There's an iterator over all the elements. There's an iterator over all the elements. That means we have big O (n) notation. The more elements you put in, the longer this task runs. Together with a nice other bug, this is fairly bad. Does anybody know the difference between scheduled executor service at fixed rate or schedule at fixed rate and with fixed delay? No? Okay. So scheduled executor service, I think everybody knows that, right? It does these nice scheduling things for tasks. If you use scheduled executor service with fixed rate, it will not wait until your task is done. It will just wait the time and submit. If you use with fixed delay, it will wait until the first one, well, the last one is done. We'll put the delay on top and we'll start the next one. So imagine you have a task that has a big O (n) runtime and grows linearly, and you submit that at fixed rate. What happened is eventually our system crashed with like 60 expiration threads doing the work and nothing else happened. So I guess that no customer up to that point used expiration. I hope it is. Okay, actually it was a track. So back to our topic, we have custom built caches. These were the typical ones in the past. Then some came up with proprietary caches, Terracotta, the good old DSO system. What was it, data ship objects or something? Then we had open source, EHCache. It was forked by Terracotta at some point. The original creator of EHCache is now our CEO. He left Terracotta last year, and came to Hazelcaster because it was bored. We have the pure commercial ones. This is like Apache coherence, yeah. Oracle coherence, open source, by the way, Hazelcast. We have InfiniSpan from Red Hat or JBoss. There is now Geode, Apache Geode, which was Jumpfire in the past, and there is Grid Game, which is now called Ignite, Apache Ignite. So Apache has now two projects doing the same thing. Well, fair. And this is the term that someone told me at a conference. One person that actually doesn't use Oracle anymore, he said they're stupidly expensive ones, which in cases, this case. So back to the JCP topic. Since we do a small JCP tour, why I'm talking about caches? Well, Hazelcast is one of the new JCache providers. And JCache is JCP standard, the new JCP standard for Java cache. It took a fairly long time to develop. It started in 2001. Just 13 years, I mean, that's forever was the same amount of time. It was just worse from design. But actually what happened with JCache, it was abandoned for a long time. It was taken out again in 2012, I guess. Something like that. And JCache tries to unify all those APIs that are currently available. So there's Oracle Coherence, which has its own, totally own API. Terracotta EHCache should never the same API because Terracotta abandoned DSO and used the EHCache API from their own system. Okay, fair enough, you have two systems. InfiniSpan has their own API, which is totally different from anything else. Hazelcast shares a lot with the Java Concurrence collections API, but we have our extensions on top of it because it doesn't always make sense to have a map put which returns the old value. Imagine you have, as I said, 100 megabyte value. Do you really want to transfer the old value back if you don't need that? No, you don't. So what Hazelcast has, we have imap.set, which just puts the value but doesn't return anything. JCache has exactly the same ideas. So all the other vendors came up with similar ideas. But a lot of things doesn't make sense in a distributed environment, and especially not for caches. So the cache interface from JCache looks fairly similar to a map, but it isn't exactly the same. So you have cache put, which doesn't return a value. If you want to have the old value, you can still say get and put. So you can tell the cache API, hey, I want the old value, but this 0.01% of people that really use that can write those want that seconds. I guess from my personal experience, I've never used return. Put if absent, yes. Put not really. Was anybody ever interested in a put return value if there was an old value or not in a non-atomic operation? I'm not. Maybe it's just me. Okay. I think from me personally, I think JCache is a very, very big success. It still misses a lot of features. Maybe I'm biased. I was part of the expert group. But I see that we still miss a lot of features. There is no transaction support, there are no asynchronous methods yet. But for Java 1 this year, so in a fairly reasonable amount of weeks, there's a plan to set up, to start version 2, which will add a lot of those missing features. And we hope it won't take another 30 years to get this version out there. So now everybody can see it, the small shameless plug on Hazelcast. Just, I guess, 4 or 3 slides. Hazelcast did 5 facts, as I said, Java Collections API, Java Concurrency API. Concurrency API doesn't only mean executor service. We have atomic longs, we have semaphore, logs, all those things you would expect. It doesn't mean you have to use those things. If you implement very, very multi-threading or very distributed system or multi-threading system, you don't want to use slots because it works against concurrency. Obviously, it doesn't make big difference in distributed systems. So yeah, still have the same problem. You just have more threads and more nodes. But sometimes locks are useful as a last resort around some operation, where you know there's normally no contention, but for the case that this 1% contention happens, you will not have last resort. Fair enough, there are use cases. Transparent data distribution, we've seen it. I just put data into the map. As long as you can tell Hazelcaster how it's serializable, whereas how to be serialized, we are fine with that. We support Java serialization in any kind of way. We have our own serialization, and we have interfaces where you can apply anything. Apache Drift, Apache Avro, Protobuf. I guess I've seen everything so far. It's a drop-in replacement for most of the Java collections APIs. A few methods have a slightly different contract because we had to break the map contract for distribution. Those methods are haven't overridden Java docs, so sometimes you really have to make sure that you read the right one. And Rod Johnson, does anybody know Rod Johnson? Spring creator?
Yes.
Yes! Oh, you, sorry. Yeah.
Yes.
He's one of our board members. He once said Hazelcaster is disruptively simple. And I think everybody had this wow effect with the just three nodes that start up. That is exactly what we want to prove to developers. As I said, distributed computing is entirely. So for me, that means time to be happy because we're Apacheizing. We have an enterprise version on top of it, but 99% of the system is open source and will stay open source forever. If you want to store terabytes of data in the JVM, we have a solution for that, but please pay us. And therefore, I don't promote the Hazelcaster.com, but Hazelcaster.org. This is the open source community. Just go in, see who's Hazelcaster heroes. We just have 2 at the moment, but one of them had written a nice book, Getting Started with Hazelcaster. It's just out in version 2. It's not me, therefore it can't be on my slide. But with that, I say you can do it. And I was so close to putting a picture of Brazil versus Germany. I wanted to make friends, so I just put a German picture. And I say thank you. By the way, you can get a free T-shirt. Just put in your name and address. We ship it to you. And if somebody's interested, we are hiring. Yeah.
What do you think is the best serialization to be used when you consider performance?
You mean which serialization mechanism? Wow. Okay. Which serialization mechanism is the best one? Obviously not Java. Not Java serialization. Externalizable is better, but still not fairly good. Hazelcast has 2 very nice options: data serializable and identify data serializable. Data serializable is fairly similar to externalizable. It still stores the class name in the byte string or in the resultant string, whereas identify data serializable maps class names to IDs. So the string gets compactor, and if you have long class names like Spring, it definitely saves you a lot of storage. From external systems, Trio is very good. It's sehr gut, yeah. Nice English. Protobuf has amazingly good results, but it has a different approach. You have to create these structs externally, and you have to run the generator. But after that, it has a very nice speed. But yeah, if
you want to have less overhead, Creo is really nice. There was someone else, I guess. No? Okay.
One more question.
Yeah.
What do you think of performance using grid-case and Hazelcaster? Grid-case pairs using grid-case. I want to search for attributes in a class that is stored in a cache. Let's say I wanna look in my cache. Every cluster which the name starts with the letter R. Great. Yeah.
Okay. Yeah, so for Hazelcast, we have a very simple index at the moment. So you can just run it without indexing, which means we have to deserialize, well, depending on your query, every key or every value. You can set up indexes, which are a nice skill improvement if you use them correctly. The problem at the moment is Hazelcast doesn't have a query planner. So that means if you have 2 indexes and the first one just returns 5 results and the other one 1 million results, you should take the one with the very first. This is planned to be fixed in I guess in 3.7 hopefully. So we get a very simple query planner that tries to estimate those results and change